On Christmas morning 2021, a mighty rocket burst into life. Quickly climbing away from the ground, it soared into the cloud-laden sky and headed for the darkness of deep space. Its target was 1.5 million kilometers from Earth, at a place where the gravities of the Sun and our planet combine in a very particular way. In this spot, known as a Lagrange point, the payload would be held in space, fixed in relation to the Earth as it circles the Sun. Once in location, this payload began its delicate deployment. Immense sheets unfurled to shade it from the glare of the Sun, as hexagonal mirror segments unfolded and clicked into place. It then waited until it cooled to the frigid background of space. After several months, the device was ready for operation, the latest in a long line of technological leaps. A signal was sent from the Earth for this most recent observer to awaken, to open its eyes and peer into the darkness. After 30 years and $10 billion, the James Webb Space Telescope had finally arrived. James Webb possesses a 6.5-meter mirror and cameras tuned to see in the infrared. Its mission is to map the lives of young stars in our own Milky Way and hunt for life on planets in orbit around other suns. But it was its view of the early universe that caused the first controversy. The power of James Webb, sitting far from the glow of the Earth, is its ability to peer far back in time. Its sensitive instruments can discern light that has traveled for more than 10 billion years, emitted by the first stars in the first fledgling galaxies. Through Webb's eyes, we can witness the birth of the universe. Astronomers, of course, had expectations of just what Webb should see in the infant cosmos. Over the 20th century, they had come to realize that galaxies, even our own Milky Way, had grown over time. They start as small groups of stars, but through collisions and mergers, small galaxies grow larger until, over many billions of years, galaxies with hundreds of billions of stars appear in the cosmos. But as astronomers pored over the new images from James Webb, something did not seem right. As they peered into the epoch of the earliest stars, they expected nothing but small, featureless blobs. Instead, they saw something unexpected. Large, well-formed galaxies peeking out of the darkness, objects that made no sense. For since the turn of the 21st century, astronomers have believed themselves to be in an era of precision cosmology. They had determined that gravity in the universe was dominated by a strange dark matter, and the expansion of the universe accelerated due to an even stranger dark energy. Both of these have fed into the most accurate model of the universe we have, a model known as lambda CDM. And yet, James Webb had revealed large galaxies appearing to exist in the first billion years of the life of the cosmos, going against the predictions of this hard-fought model. Some scientists have been driven back to the drawing board to revise their theories of galaxy formation. But others, much more worried, fear for the very foundations of our understanding of the universe. But this is not the first time that new eyes on the sky have demanded a revision of the cosmos. Since the earliest of times, people have looked to the stars to uncover the workings of the universe. And since the earliest of times, they have been surprised by what they saw. And so, what do we understand about those first galaxies forming in the black just after the Big Bang? And do these surprises thrown up by James Webb derail our understanding of the universe, or help strengthen its foundations even further? The story goes that Galileo Galilei was the first to successfully turn a telescope to the skies. The device, a simple arrangement of lenses, had only recently been invented. Its earthly employment having mainly been navigation, surveying, and of course warfare. But Galileo's focus was the motions of the heavens. The invention of the telescope is implicitly tied to the birth of modern science. A little more than half a century after Galileo, Isaac Newton also turned his attention skyward. Replacing lenses with a silvered mirror, he revolutionized the design of telescopes, sharpening the image and constructing the forerunner of today's massive telescopes, including James Webb. But unlike Galileo, Newton's observations didn't revolutionize the cosmos. His discoveries of the laws of motion and gravity certainly did. Now, the orbits of planets, moons, and comets were understood not to be a sign of the divine, but the results of physical laws that pervade the entire universe. Astronomical telescopes steadily developed after the time of Newton, and through each advance, more and more light could be collected. The improvement of optical systems resulted in clearer and sharper images. Astronomers now had the tools to reveal the true beauty and complexity of the universe. And so, just what did they see? As well as stars and planets, the skies were often home to magnificent comets. By the mid-1700s, French astronomer Charles Messier was hunting for these heavenly bodies. He was looking for the fuzzy coma of a comet, formed as ice and dust boiled off the cometary surface. But in his search, he found himself constantly frustrated. We now know that comets are rocky, icy bodies that orbit the sun, and Messier had expected the fuzzy coma to move night after night during the comet's travels. But he came across numerous fuzzy objects that stubbornly remained in place, not changing at all. Messier decided to allay his frustration by cataloging all these anomalies, ignoring them if he happened to spot one. And so, though Messier's catalog of 110 objects mainly contained simple clouds of gas within our Milky Way, unknown to Messier, many of his objects were much more distant. Throughout the 19th century, with better telescopes, astronomers had found structure in some of Messier's objects, swirling spiral patterns, hinting the objects must be rotating. Eventually, two giants of astronomy went head-to-head to settle the question, and by 1921, a great debate on the nature of these spiral nebulae began. The protagonists were Harlow Shapley and Heber Curtis. In Shapley's mind, our own Milky Way was the entire universe, whilst Curtis argued that they were extremely distant, individual galaxies lingering out there. Though the debate ended in stalemate, very soon the question would be settled once and for all. By the 20th century, telescope mirrors had grown to more than a meter in size, and in the 1920s, Edwin Hubble used the 2.5-meter Hooker telescope to survey the heavens. It was then that the scale of the cosmos grew immensely and definitively, as he proved that spiral nebulae lay far beyond our Milky Way, whilst the flow of galaxies away from us showed we live in an expanding universe. In a few short years, our view of the cosmos had been completely revolutionized and rewritten. Countless galaxies, each with billions of stars, were scattered across the universe in a cosmos no longer seen to be unchanging and eternal, but a dynamical place, expanding and evolving, springing into existence at some time in the past. The story of this Big Bang, our cosmic birth, has been told many times, and after the universe's fiery creation, we understood it was smooth and featureless. But this still left a question. Where did all the galaxies we see today come from? Just what forces sculpted the universe? Throughout the 20th century, telescopes continued to grow and scour the cosmos. More mysteries were revealed. Dark matter and dark energy amongst the biggest. By the dawn of the 21st century, 10-meter telescopes now stared into the darkness. These earthbound telescopes were complemented by telescopes in space, the most famous of these being the Hubble Space Telescope, put in orbit in 1990. Its mirror, only 2.5 meters in diameter, is small compared to the behemoths on Earth. But sitting beyond the shimmering effects of the atmosphere, it can see more clearly than the others. Over the last 3 decades, the sharpness of Hubble's observations has wowed both astronomers and the public. And posters of spectacular images are stuck to walls all around the globe. But not long after Hubble was placed in space and opened its eyes on the universe, plans for its replacement, a bigger, more powerful telescope, were put in motion. The mission had to be ambitious, pushing the limits of technology and striding past the view of Hubble. The planned mirror was to be so large it wouldn't fit into even the largest rocket, so it would have to be segmented and folded like scientific origami. And one of the most powerful rockets would be needed to fling it into the darkness of space. Through numerous delays and cost blowouts, this new telescope, the James Webb Space Telescope, found itself on the launch pad. And on that Christmas morning 2021, it blasted away from the Earth. Astronomers have pinned their hopes on this $10 billion feat of technology and science, hoping to conclusively answer the biggest question of all. Just where did galaxies come from? How can you use a map of the universe to chart a course through the center of an atom? The James Webb Space Telescope is the latest in a long line of telescopes we've sent skyward, but it is not the strangest. That prize could well go to the Planck satellite, launched in 2009, and for its 3 years of operation, the coldest known object in outer space at 0.1 degrees above absolute zero. Its mission was not to look at stars or galaxies, but to map the entire sky. And counterintuitively, scientists have been able to scale down this multi-billion light-year wide map to plot the microscopic world, revealing the landscape of the beginning of time. Planck was the latest in a long line of satellites used to map out the cosmic microwave background, CMB, the leftover radiation from the first moments of the universe. This had been discovered in the 1960s, and Planck's goal was to hunt for ripples in this all-sky emission, tiny variations in the temperature of the cosmic microwave background across the universe. The temperature of the cosmic microwave background is about 2.75 degrees above absolute zero. But soon after its discovery, there were hints that this temperature was not the same everywhere. At about 1 part in 100,000 in temperature difference, this pattern of ripples was formed in the earliest moments of the universe, imprinted when the cosmos was extremely different to that we see around us today. And yet, despite this vast chasm of time, these ripples are essential for our very existence, as they reveal the ultimate origin of galaxies themselves. To seek out this origin of galaxies, we have to go back a very long way, back to about 10 to the minus 36 seconds after the universe came into being, when it was nothing but a roiling sea of energy and particles. At this time, astronomers think that the universe drastically changed. The trigger is uncertain, but for the briefest of periods, the expansion of the universe exploded. Cosmologists call this violence inflation, an event that flattened the very space-time geometry of the cosmos. But by 10 to the minus 32 seconds, it was all over, and a more sedate expansion resumed. The expansion of inflation froze and emptied out the universe. But as it came to a close, the immense energy of inflation flooded back into the vacuum. And out of this emerged matter and radiation, electrons, photons, and quarks, smoothly filling space with the stuff of today's universe. But not totally smoothly, for there were tiny, almost imperceptible ripples in the cosmos, ripples that would end up being crucial for our own existence. For gravity reached out from these overdensities and began to draw in other matter. And it was these tiny overdensities that would become the gravitational seeds of the galaxies we see today. But where did these ripples come from? How far back does this origin story go? To understand the ultimate origin of galaxies, we have to pull the veil back on the very earliest moments of the cosmos, the time before inflation. In these opening moments of time, quantum mechanics reigned supreme. At the smallest scale, much smaller than the scale of an atom, quantum energy churns and roils, fluctuating in and out of existence itself. These fluctuations are unpredictable, governed by the probabilistic world of the quantum, and defined by Heisenberg's uncertainty principle. This principle says that energy can spontaneously appear from nowhere, as long as it rebalances and pays back its energy debt in the appropriate timescale. But the onset of inflation broke the harmony of this quantum loan system. The rapid expansion cut off the repayment, and the quantum ripples in energy are frozen into space. It also inflated the size of the ripples from microscopic to macroscopic. And at the end of inflation, it's these ripples that are filled with the matter of the cosmos. And this is how we can use a map of the entire universe, the cosmic microwave background, to investigate the microscopic quantum world. Despite these vast changes, by the close of inflation, the universe was still very young, and as it cooled and expanded, it continued to evolve. At a millionth of a second, protons and neutrons solidified out of the particle soup, and at the 1 second mark, these began to combine into the first elements. By a couple of thousand seconds, these first steps of the universe were complete. The universe had expanded and cooled, and the nuclear furnace was extinguished. Slowly, these fires of creation faded and died, and the universe was plunged into an inky blackness. These dark ages would envelop the universe for 100 million years. But just like the dark ages of early medieval Europe, they were far from uneventful. Gravity's grip had grown tighter as matter flowed from the less dense areas into the denser regions. But just what was it flowing in the darkness? Of course there was the subatomic soup of hydrogen and helium nuclei, along with electrons, photons, and ethereal neutrinos. But hidden in the black, there was more. Much, much more. For as well as atoms, the Big Bang had created huge quantities of other matter. Matter that still dominates the mass of the cosmos today. In the darkness, dark matter had started to flow. As this strange dark matter dominated the gravitational pull of the universe, in the early universe, in the darkness, it was dark matter pooling into the overdense regions. The gravitational pull of dark matter was irresistible, drawing in nuclei, electrons, photons, and neutrinos. In the darkness, dense regions grew, and the first whispers of galaxies had truly begun. But normal matter followed a different path. Unlike dark matter, whose physics is extremely simple, gas is extremely complicated. Gas can collide and shock, heat, and, importantly, cool. And so, when the universe was about 100 million years old, the gas was dense enough and cool enough to finally fragment. These fragments collapsed under the continuing action of gravity. As they collapsed, the density of the fragments grew. As they became more spherical, the temperatures of the cores of these fragments soared, and nuclear reactions ignited. Finally, the first stars in the cosmos were born, and light began to trickle back into the universe. However, these first stars were quite different to their modern-day counterparts. They were purely hydrogen and helium, and enormous. Many were more than 100 times more massive than our sun. They would burn bright for a few million years before dying in supernovae. Despite these brief lives, their intense light, mainly ultraviolet and X-rays, changed the universe once again. This radiation spewed into the cosmos, lighting up the heavens. But as well as this, as their high-energy photons smashed into the immense clouds of surrounding hydrogen, they tore their electrons clean off, reionized the universe. More and more of the cosmos was transformed back into plasma, a situation that remains today. 99.9% of all atomic matter across our universe is in the form of superheated plasma. As these first generations of stars burned through their deaths, they polluted the universe. In their nuclear hearts, heavier elements such as carbon and oxygen had been forged. Through their explosive demise, these elements had been thrown into the black. The chemical enrichment of the universe was truly underway. And yet, throughout all these changes, gravity never changed, never faltered. It continued to draw matter together, and inhomogeneities continued to grow. Eventually, groups of stars fell together, merging and forming larger groups of stars. The epoch of the first galaxies had arrived. It's impossible to pinpoint exactly when a galaxy is born. Mass overdensities seeded by quantum fluctuations are continuous, and whilst punctuated by the first stars bursting into life, the process of galactic growth continues inexorably. But grow they do. Firstly, through a steady accretion, and then through collisions of more appreciable chunks of matter. Cosmologists call these chunks hylos, dark matter, gas, and stars, bound by their mutual gravity. And as time goes on, scattered throughout the universe, more massive, gravitationally dominant halos emerge. These dominant halos become the site of future galactic growth. And as their gravitational influence grows, so did their dominance. More and more matter is drawn into their grasp, providing the raw material for building future generations of stars. These initial stages of galactic growth were quite uneven. The majority of these baby galaxies were small and growing slowly. More massive and intense galactic growth was much rarer indeed. This immense spread of galaxy masses is still imprinted on the universe today. And for the smallest of galaxies, these initial stages of life were quite dangerous. They could potentially host a massive star burning brightly for a few million years, only for it to supernova, with the violence of its death expelling all other gas in the galaxy. The small galaxy's weak gravitational pull losing this gas into the universe. Its star-forming life ended before it had barely begun. Many of these small but extinguished galaxies would have inhabited the early universe. Halos of dark matter, devoid of all atoms and of all stars. These dead, elusive ghost galaxies were doomed to remain dark and unseen, and they should still fill our universe today. But more massive galaxies were different. In a larger galaxy, gravity could draw the gas back in, being recycled into the next generation of stars. And so, whilst many galaxies were snuffed out in the early cosmos, others grew fat on the stars and gas they continued to consume. In their deep gravitational wells, new stars were born, lived, and died. But these were different to those of the first generation of stars. Through each generation of stars, heavier and heavier elements are expelled and pollute the cosmos, and these are recycled into subsequent generations. These elements represent barely a trace compared to the dominant hydrogen and helium, but their presence drastically influences the life cycles of their hosts. The heavier elements mixed into the layers of the stars change their opacity. This is a measure of how easy it is for the nuclear energy at the stellar heart to escape. And entrapping radiation, stars more similar to our sun begin to be born, with longer lifespans and less explosive ends. As billions of years passed, some galaxies began to settle into a more sedate lifestyle, but violence still existed in the universe. A violence that began at the very start of violence that would go on to create some of the most extreme environments in the cosmos. To understand these, and how the first galaxies became the galactic zoo we see today, we will have to first take a trip back to the middle of the 20th century, to a time when astronomers were facing a mystery on a truly cosmic scale. Carl Jansky was confused. It was 1932, the early days of transatlantic radio communication. The world was getting used to beaming voices over thousands of kilometers. But there was something about the signal he heard on these transmissions that troubled Jansky. A persistent background hiss? Though it wasn't the existence of this background static that befuddled him, but its immaculate timing. Jansky had found his static varied with the time of day, differing in intensity on a regular schedule. How was this possible? How could his electronics know what time of day he was taking his measurements? Even stranger, as his observations spun out over days, weeks, and into months, he noticed that the static was not quite aligned with the 24 hours of the solar day. The timing of the varying noise changed slowly but steadily, drifting across the sky, appearing to be in sync with the sidereal day, the time taken for distant stars to circle the Earth. The difference was small, just 4 minutes, but the implications were profound. For it meant the source of Jansky's radio noise lay well beyond the Earth and the Sun, and resided deep in the heavens. At the time, many astronomers were scouring the skies with their telescopes, focusing on the optical light they knew arose from stars and galaxies. But Jansky realized that another electromagnetic radiation was arriving from the universe, and the era of radio astronomy was born. Unfortunately, Jansky would play no further role in establishing the groundwork. Having identified the source of the radio noise, his employer, Bell Labs, set him other jobs to do. But his name is remembered, used now as a unit of intensity of radio waves from the sky. With the announcement of radio waves from space, others took up the mantle. Soon, radio waves from the sun were detected in the UK and the US. In the US, Grote Reber built the first true radio telescope, was the only radio astronomer for a decade, and made it clear that our own Milky Way glowed in this new light. But that was not all, for later maps of the radio sky showed there were many more sources. There were powerful radio emissions radiating from small points all over the sky. And so, the first quasi-stellar radio sources, or quasars, began to be found. Astronomers now know of more than 1 million quasars spread throughout the cosmos. They've been discovered to be powered by supermassive black holes with masses more than 1 billion times that of our sun, and are so powerful we can see them from vast distances away and back in time, over more than 10 billion years. These supermassive black holes are thought to have perhaps formed from the deaths of supermassive first stars, and after feeding voraciously and merging, became the central gravitational point of many larger galaxies. And so, for the first few billion years of the universe, it burned with activity. The fires of the first stars, the first galaxies, and the first quasars shone brightly. But after this first age passed, the vigor of youth began to wane, and cosmic activity began to calm. The universe settled into a more sedentary life. However, over the last 10 billion years, though the rate of star formation has steadily declined, galaxies have continued to evolve and change, driven by the endless pull of gravity. Small galaxies have steadily grown into large galaxies as they have accreted more stars and dark matter, and large galaxies have grown even larger, feasting on their cosmic neighbors. Some galaxies have been completely shaped by their spin as cooling galactic-scale gas has collapsed into a flattened pancake, which fragmented into stars. This immense disk of stars, rotating steadily, has become the defining feature of these galaxies, the beautiful spirals we spy through our telescopes today. But for other galaxies, their journey to spiral beauty has been cut short, as collisions between more massive galaxies have violently torn them apart and robbed them of their spin. Instead of settling into rotating disks, they are transformed into more formless objects, elliptical galaxies, the other major galaxy type spied in the heavens. And these elliptical galaxies are a foreshadowing of our own galactic destiny. Elliptical and spiral do not capture all the designs of galaxies we can see, and astronomers have a further classification, the irregulars, to capture the rest. These misshapen galaxies appear to be suffering the scars of more recent galaxy interactions, and so they are caught maybe mid-transformation before they finally settle. Astronomers estimate there may be 1 trillion galaxies lying in the observable universe, coming in a wealth of sizes from tiny to immense. Most galaxies are small, with only a handful of billions of stars within, whilst the largest we know of is more than 200 times more massive than our own Milky Way. One of the most startling discoveries of the last century was not only the galaxies themselves, but also the realization that galaxies are not simply scattered randomly throughout the cosmos. Through the action of gravity, the quantum seeds that are imprinted at inflation are shaped into a complex network of mass known as the cosmic web. Volumes of underdensity are emptied out, with matter drawn towards more massive regions. While some galaxies and dark matter remain, these sparse regions can extend for millions of light years. The outflowing matter gathers into immense sheets and filaments and continues to be drawn towards the most massive objects in the cosmos. But just where are all these galaxies heading? On their journeys out of voids and through the sheets and filaments. In this complex network, in which dark matter is distributed like a sponge, there are superdense regions. It is these massive regions that are the ultimate gravitational goal of all mass. These are the clusters of galaxies. Galaxy clusters are incredible places, some home to many thousands of galaxies. These galaxies slosh about in immense halos of dark matter that vastly outweigh all of the stars, the greatest concentration of mass in all of the universe. And at their hearts sit truly immense monsters. For it is here that the most massive galaxies seen in the entire cosmos grow. These cluster center galaxies, disappointingly named CD galaxies, are true giants of the universe, built from hundreds of trillions of stars, enveloped in a massive quantity of dark matter. Cosmic behemoths, they sit deep within the well of gravity and are circled by thousands of other galaxies. Zooming out even further, astronomers have found that clusters themselves cluster together, group together into even more immense structures they call superclusters. In our patch of the universe, we appear to be embedded in the Laniakea, home to many millions of galaxies. Although the question of whether gravity holds superclusters together remains up for debate. Just as galaxies come in an immense range of sizes, so do the clusters of galaxies. And even for each of the smaller clusters, there exists a myriad of galaxy structures. These are the groups. Most galaxies in the universe live in such groups. They are typically home to 1, 2, or a handful of larger galaxies, similar in scale to our own Milky Way. With them will be a host of smaller galaxies, possibly hundreds of dwarfs, all bound together by their mutual gravity and that of the dark matter that accompanies them. In fact, our Milky Way lives inside such a group we share with the Andromeda Galaxy. And this local group, as it is known, contains a wealth of other galaxies. Some of these are visible to the naked eye, namely the Magellanic Clouds seen in the southern hemisphere. But more than 100 other galaxies are held in the gravitational grip of this local group. Most of these smaller galaxies have only come to light in the last few decades, revealed in deep surveys with new telescopes that peer even deeper into the darkness. And the presence of all these dwarfs orbiting amongst the larger galaxies told the astronomers something important, that the epoch of galaxy evolution is far from over. Rodrigo Ibada was a young graduate student working towards his PhD at the University of Cambridge. He was studying at the world-renowned Institute of Astronomy, founded by the famous cosmologist Fred Hoyle. His research was focused on understanding the dynamics of stars near the galactic core. But to do this, he needed the power of a telescope more than 15,000 kilometers away. Just outside the small country town of Coonabarabran sits the Siding Spring Observatory, home to a number of telescopes. In the early 1970s, it saw the opening of the Anglo-Australian Telescope. With a 3.9-meter mirror, it was state-of-the-art for its time, and it still leads the world today with unique instrumentation. Rodrigo had traveled to Australia to measure the speeds and chemistries of stars in the central galactic bulge, using the power of an instrument called 2DF, 2-degree field, mounted on the Anglo-Australian Telescope. With a combination of optical fibers, 2DF could look at more than 50 stars at a time. And so, in a few nights, Rodrigo could survey various observational fields across the bulge. Astronomers rarely make discoveries when sitting at the telescope. The raw data they take usually requires processing and analysis to reveal its secrets. With the proto-internet of the early 1990s, this meant carrying your data home on tapes. And Rodrigo set to work under the often cloudy and rainy skies of the fens of Cambridge. Astronomers had made predictions for the speeds of stars in the central regions of the galaxy, expecting stars to be zipping around on random orbits, unlike the circular paths in the galactic disk. And in some of his targeted fields, this is just what Rodrigo saw. But in some fields, however, Rodrigo was presented with a puzzle. Stars in the galactic bulge were still there, zipping back and forth. But there was something else. Stars all moving together. Stars whose origin could not be in the center of our Milky Way. Like most astronomers, Rodrigo's first conclusion was that he had made a mistake somewhere in his analysis. Perhaps he had measured the speeds incorrectly, or missed something in the predicted motions. But eventually, when he had ruled out all other possibilities, he had to conclude what he saw was real. Just what had he uncovered? Together with his supervisors, Jerry Gilmore and Mike Irwin, he came to a radical conclusion. The stars he was seeing were simply not part of the galaxy. These stars were intruders into the Milky Way, falling in from somewhere outside. What Rodrigo had found was the Sagittarius Dwarf, a small galaxy crashing through our own. The Sagittarius Dwarf was hidden in plain sight, with its feeble light spread over a huge area of sky. And when Rodrigo pored over old photographic images of the galactic center, its image steadily emerged. It was clear from its appearance that it was being tidally disrupted by our own galaxy's gravity, and in a few billion years, Sagittarius would be completely destroyed, its stars added to our own. Since the 1990s, it was realized that Sagittarius was not a unique event, and that the Milky Way is consuming a number of other dwarf galaxies and is constantly growing. Andromeda is also wrapped in the tidal debris of recently consumed dwarf galaxies. The feeding that began many billions of years ago is continuing today. Astronomers call this phenomenon galactic cannibalism. And so, we bring our understanding of the universe up to the present day and our superficially calm lives within the fully grown Milky Way. Astronomers like Rodrigo have built their observations on the shoulders of giants. Previous generations of astrophysicists and cosmologists working together to model and test how galaxies work, and reaching back in time billions of years to theorize how everything came to be. And yet, if you were to believe the headlines in 2022, all of this, from quantum ripples to theories of galaxy formation, may have been fundamentally wrong. This story opened with the mighty roar of a rocket on a Christmas morning, and a new view of the universe shocked astronomers. Galaxies that appeared to be far too large, too grown up, blinking back at us from the first billion years of the cosmos. One scientific paper even started its title with "Panic at the Disks," highlighting the shock that well-formed disk galaxies appeared in the infant cosmos. Soon, newspapers all around the world were announcing that the James Webb Space Telescope had brought an end to cosmology itself. Was our entire understanding of galactic formation under threat? Around the globe, cosmologists gnashed their teeth at the media attention and leaped to clarify what Webb had seen and what its observations really meant. And so, to understand this, we are going to have to delve into our current model of the cosmos, because it all boils down to one key question: what kind of universe do we live in? As many scientific stories do, we begin in the early decades of the 20th century. Einstein had thrashed out his general theory of relativity, our modern theory of gravity, and with others such as Friedmann and Lemaitre, the equations that governed the cosmos were derived. These showed that the universe should be a dynamic place, expanding and evolving as it aged. In the 1920s, Hubble's observations showed this math was an accurate description of reality, that galaxies were moving away from each other due to the expansion of space. And as galaxies must have been closer together in the past, there must have been a time where everything was together, a cosmic creation. Our modern cosmology, the Big Bang, had arrived. The relativistic cosmological equations, however, do not predict a single, specific universe. In fact, there are an infinite number of possible universes mixed in the mathematics. So to single out our universe, astronomers needed to measure two specific things about the universe. Namely, how fast is it expanding now, and just what does it contain? The measured rate of expansion is known as the Hubble constant, and it tells you how quickly galaxies are moving apart based on their current separation. The separation of nearby galaxies is slower than those further apart, as there is more expansion of space between the two distant objects. Measuring the Hubble constant was a major observational effort of the 20th century, with astronomers forming factions around particular techniques and measured values of the constant. The process was complicated, as accurate measurements of galactic distances were required, and as the universe doesn't provide us with cosmic rulers, these were notoriously difficult to measure. For half a century, debate raged over whether the Hubble constant was 50 or 100 when expressed in cosmologists' favorite unit of kilometers per second per megaparsec. But by the 1990s, the power of the Hubble Space Telescope was brought to bear on the problem, and astronomers breathed a sigh of relief when the measured value was shown to be 72, about 235 kilometers a second per million light years. So with one of the key values determined, what about the content of the universe? This was an essential ingredient, as the presence of matter and radiation drag on the expansion and steadily slow down the cosmos, with more material providing more of a deceleration, as this influences the age of the universe. Astronomers were keen to measure just how much stuff there was. Counting starlight was relatively easy, as you can simply peer through your telescope and see the galaxies. But astronomers had come to realize there was more to the universe than the stars you can see. Observations of the rotations of galaxies and motions in clusters of galaxies showed there was much more. The mass of the universe was actually dominated by unseen dark matter. As dark matter is almost impossible to observe, astronomers decided on another path. They would chart the cosmic expansion as they peered into the distant universe, and by mapping this, they could determine just how much dark matter is pulling on expansion. By the 1990s, two teams set out using the light of exploding stars as beacons to do just this. The High-Z Supernova Search Team and the Supernova Cosmology Project. The observational challenges were substantial, again requiring accuracy to make the measurements. Their focus was supernovae 1A, stars whose explosions appeared to be essentially identical, allowing them to calibrate their true brightness and so measure distances. As the new millennium approached, they had their chart of the expansion history of the universe. But as they stared at the data, the astronomers were confused. They had expected, due to the presence of matter, the cosmic expansion should have steadily slowed. But whilst this had been the case in the early universe, in our time, it was not. And so they were faced with the question of what could be driving the expansion faster and faster. Looking at the relativistic equations of the cosmos, the culprit couldn't be matter or radiation. Something else would have to be added to the universe, a new form of energy throughout space. And this energy would have to have properties unlike matter or radiation, making it push rather than pull on expansion. This mysterious substance, not previously seen in observations, was dubbed dark energy. But it was not only the presence of dark energy that shocked astronomers, it was also the amount. They found that all matter, luminous and dark, accounted for only 30% of the cosmic energy budget, with this ubiquitous dark energy accounting for the other 70%. And as atoms in the form of stars, planets and gas make up about 5%, we truly live in a dark universe. Astronomers had isolated our universe from the myriad possibilities, the infinity of options. We finally knew what universe we lived in. They called this the Lambda CDM cosmological model. Lambda signifying the presence of dark energy, while CDM stands for cold dark matter, the material that shapes the formation and evolution of galaxies. And it was with this they could precisely pinpoint the moment of creation, a Big Bang, 13.8 billion years ago. With the Lambda CDM cosmological model in hand, we can calibrate the universe. Light from distant objects is redshifted due to the expansion of space, and we can tie this redshift to the age of the universe when the light began its journey. Indeed, it is this cosmological model that tells us the James Webb Space Telescope is seeing galaxies in the first billion years of the cosmos. And so, do the observations of Webb really threaten our cosmological framework? The difficulty is that the mathematical equations of cosmology only tell us about the large-scale evolution of the universe, not what the detailed flow of dark matter and gas into the first galaxies is. To understand the growth of galaxies, we need to add more to the cosmological equations. And it is here astronomers face significant challenges, as the growth of galaxies depends on a wealth of factors. These range from scales of millions of light years, charting the flow of matter in the large-scale structure, down to observing individual galaxies and witnessing starlight through our telescopes. And we even need to add the fragmentation of gas clouds and the formation of stars into the mix. Not only this, but the first stars evolve fast and explode, blasting material and energy into the surroundings. All this needs to be tracked and traced in a swirling environment where massive black holes may lurk. Astronomers try to capture all of this complexity into a set of mathematical recipes. And these recipes represent our models of how galaxies form and evolve. But the key here is in the plural, as there is not a single preferred model to explain it all. The physical conditions and processes of the early universe are, in part, mysterious and unknown. Astronomers have to resort to approximations and even guesses in constructing aspects of their models. And it is the veracity of these models that is being put to the test by James Webb. In the short time that has passed since the claim of cosmology's demise, the excitement has died a little. Astronomers have realized that there is enough slack in their models to account for Webb's observations. A tune here and a tweak there, and the galaxies spied by the telescope are not that surprising. Astronomers may have been led astray by some of the initial assumptions that were made. Take, for example, something that is known as the stellar initial mass function. This tells us the mix of stars formed when a giant gas cloud fragments and collapses. Typically, there will be a few massive, bright stars and lots of fainter, smaller stars. But what if your stellar initial mass function is wrong? The stellar initial mass function is something we can measure and calculate in the local universe. But the assumption that it was similar more than 10 billion years ago is just that, an assumption. We know that at the early times, the universe was very different from today. And so, what if the stellar initial mass function was also different? What if it was skewed and resulted in the birth of more luminous stars than expected? Then these baby galaxies would burn more brightly than expected, and astronomers would estimate that they are larger than expected. At the moment, not everyone is satisfied. But the feeling is, there is a problem with models of galaxy evolution. The underlying cosmological model, lambda CDM, appears to be safe. Indeed, if James Webb is telling us anything, it's that the early universe was more complicated than we have so far imagined. And this is precisely what it was designed to do. You've been watching the entire history of the universe. If you enjoyed this journey, make sure to like and subscribe to Stellify Science. Drop a comment below and let us know what you think of James Webb's revolutionary discoveries. Thanks for watching. I will see you next time.